Hello class, in this video we are going to be talking about the magnetic effects of electric current. This is our first video of the magnetic effects of electric current. So let's start with the actual video. What is a magnetic field? It is represented in the diagram here. A magnetic field is a space or region around a magnet or a current carrying conductor in which its influence can be felt by a magnetic substance. So it is basically the area around a magnet or a current carrying conductor where its magnetic effects can be sensed, where it attracts other magnets or other magnetic elements or magnetic substances. The SI unit of magnetic field is Tesla. Yes, we can measure magnetic field. And magnetic field is a vector quantity because it is dependent on both magnitude and direction. If you don't know what a vector quantity is, it is a quantity that is dependent on both magnitude and direction, not only magnitude. So the value varies from direction to direction, and it can also be negative. Now let's move on to the next point, which is that it is represented by magnetic field lines. In the diagram below, you can see magnetic field lines clearly. The magnetic field lines are the lines around the magnet, as you can see in the diagram below. Let's move on to what magnetic field lines are. So as you can see in the diagram here, magnetic field lines go from North Pole to South Pole outside the magnet, and inside the magnet they go from South Pole to North Pole. Okay, they basically move in cycles around the magnet. They move in both directions, and they always move in a specific direction. They can never cross each other. Well, that is pretty obvious actually. They are not always equidistant from each other. There are infinite magnetic fields at a point, but they never cross each other. They are parallel to each other at some points, but they never cross each other. Now let's move on to an activity. This is the activity you're going to use to draw magnetic field lines. Spread a few iron filings on a piece of A4 paper, as represented in the diagram below. Place a bar magnet just between the filings and observe what happens to the filings. Excuse me. You're going to notice that your arrangement, the arrangement of the magnetic, what do you call it? Sorry. The arrangement of the iron filings are going to look like the arrangement in the diagram below. And to make it more clear, tap on the piece of paper a number of times, politely and gently. You're going to clearly notice the pattern. It is a pattern made by iron filings. I highly suggest you try it yourselves, but I am telling you what's going to happen. The observation is that the filings will arrange themselves in a pattern that represents magnetic field lines, as you can see in the diagram below. Please try it at home for your own knowledge's sake, and it's really interesting. Let's move on to another activity. In the last activity, you saw what magnetic fields look like. You saw what iron filings arrange themselves in which pattern they do so, and everything else. In this activity, we are going to learn how to draw magnetic fields using a magnet and a compass. So place a bar magnet on a piece of paper. Then place a magnetic compass at one corner of the North Pole. Okay, you just place it at one of the corners of the rectangular bar magnet, just like you make a point in maths. Okay, observe where the needle of the compass is pointing, basically the north side of the compass, and mark the point just ahead of the needle. Just mark the direction in which the compass is pointing, and now place the compass just ahead of that point and observe where the needle is pointing now. Obviously it is going to be pointing at a different direction. That's why we are doing it. Now mark this point too, and keep on doing this until you reach the South Pole. Now join all the dots you made using this compass. Okay, join all the dots and you're going to notice a pattern. Once you're done, take the compass back to the North Pole and start again from a point behind the point you initially started with. Like don't start with a corner, start with a point a little bit beyond the corner, like in the middle of the compass, just for your own knowledge. Then carry on doing this procedure until you make more lines. And you will notice that the lines you have joined or the dots you have joined and made represent magnetic field lines. Now mark the arrows on the magnetic field lines in the direction your compass points, and you're going to basically have the magnetic field lines, and that is what magnetic field lines look like. It is really interesting practical, and I suggest you try it by yourselves. Now let's move on to the main point of this chapter: magnetic field around a straight current carrying conductor. Current carrying conductors make a magnetic field around it. Every single current carrying conductor does that. Okay, an electric current carrying conductor makes a magnetic field around it. A straight current carrying conductor makes a magnetic field such that the magnetic field lines make concentric circles. So the magnetic field lines are arranged in concentric circles. They have the same center. For those of you who don't know what a concentric circle is, the center is the point, is basically the wire, okay? It's basically the conductor. That is, you can see in the diagram what the magnetic field looks like. The arrow indicates the conductor, and the magnetic field lines are indicated by the circular loops. So, in which direction are the magnetic field lines moving, or the magnetic field lines circulating? To check this, we have to perform an activity. Make a fist with your right hand and use your thumb to point in the direction in which the current is moving. Okay, use your right hand. It's not going to work with your left hand. Okay, it's called the right hand thumb rule. So your the rest of your fingers, the index finger, the middle finger, the ring finger, and the pinky, are going to point in the direction where the magnetic field lines are circulating the conductor. Okay, the thumb points in the direction where the current is moving in, and the magnetic field's direction is indicated by the rest of your fingers. So the formula for calculating the magnitude of the magnetic field around a current carrying conductor is permeability I upon 2 pi r. The little Greek letter over there, I don't really remember what it's called. I think it's called mu, stands for permeability. Permeability is a value that changes per material. Okay, it depends on the material it is going to be given to you, so please don't worry about that. I stands for the current, as we have studied in our electricity series, and if you haven't watched that series, I highly suggest you do so, because this series is totally dependent on the electricity series. And pi is a universal constant. If you still don't know, you probably studied it in maths, and it's approximately equal to 22 upon 7. R is the distance at which you're measuring the magnetic field of the conductor. You can measure it at any distance. You can measure it at the center. You can measure it at 1 meter away from the wire, 2 meters away, and it depends on where you are measuring it from. It is going to be given to you in the question. So R is the distance at which you're measuring the magnitude of the magnetic field. Let's revise again. The mu stands for permeability. It is a constant of the material used. I is the current carried by the conductor. Pi is a universal constant, and R is the distance at which the magnetic field needs to be calculated. Now let's move on to the next point, and the next part, which is magnetic field in a current carrying circular loop. So the magnetic field around a current carrying circular loop are illustrated in the diagram above. I really don't have words to explain it, so please study them from the diagram above. As you can see, they are arranged in circles, and they are arranged in between the magnetic field, in between the loop and around the loop. So please study this. And again, you can use the right hand thumb rule, as we learnt in the straight current carrying conductor part, to check the direction of the magnetic field. The magnitude of the magnetic field in a current carrying conductor is calculated by using the formula mu I upon 2 it's not supposed to be 2 pi r, it's only supposed to be 2r. The symbols depict the same symbols as in the previous part. The mu stands for permeability, I stands for current, pi is a universal, there is no pi, sorry. And the only difference is that r stands for the radius of the loop. It's not the distance at which you're measuring it. You need to measure it at the center, so it is the radius of the loop, okay? Now let's move on to the next part, magnetic field around a current carrying solenoid. So what is a solenoid? Well, a solenoid is basically a collection of loops arranged as a cylinder. The diagram above illustrates the magnetic field around a current carrying solenoid. So the magnetic field is arranged or is concentrated in the center, and the diagram pretty much illustrates it. Okay, the magnetic field inside a solenoid is nearly uniform at all points, the part inside the solenoid. So the formula for calculating the magnetic field inside a solenoid is permeability Ni, where N is equal to the number of coils in the solenoid. I is equal to the current, as you all know, and mu is the permeability, which depends on the material. I know I was pretty nervous in this video. It's actually because I'm pretty sick and I'm not going through a very good time, and I would just like to thank you all for cooperating with me throughout this video. Thanks for watching, guys. Please like this video, subscribe, comment any suggestions you have in the comment section down below. Share this video with your friends and family. I hope you enjoyed this video. I hope you learned something new. Please subscribe to my channel. I seriously need support from you guys. I'm so desperate to show you more content. I'm going to make a few videos a week. I don't have a definite schedule. And once again, guys, thanks for watching. See you in the next part.